Today we are going to understand about the relationship between Kp and Kc. Kp and Kc are nothing but equilibrium constant. Okay, K is for equilibrium constant and P we are using for the gaseous product and the gaseous reactant. That P represent the partial pressure of gaseous reactant and product. And here that C represent for the concentration of the reactant and product. So P is for pressure. Okay, which pressure? The partial pressure. And C represents the concentration of the reactant and product. Okay, so let the example here we have when 1 mole of nitrogen gas reacts with 3 mole of hydrogen gas gives 2 moles of ammonia gas. Okay, so this is the general reaction for the representation of formation of ammonia from hydrogen and nitrogen gas. Okay, so now we had to write first what is the Kp and Kc here. So for given reaction we have first Kc. Kc is equilibrium constant of the reaction with related to their concentration or change in concentration. So for Kc we have formula the concentration of product divided by product of concentration of reactant. So I'm writing here concentration of ammonia, it is the product, so we have to write first in numerator, and whenever we are writing that square bracket which represents the concentration NH3. Okay, and here we have coefficient 2, so that coefficient 2 will go on the power, so I'm writing here 2 divide by product of concentration of both the reactants. So we have first nitrogen. Here we have only one coefficient, so we do not have to represent one here, because if we have nothing, that means we have one. And concentration of hydrogen, and we have coefficient 3, so that 3 will be on the power like this, 3. Okay, so this is relation for Kc. Now all the reactant and product at their gaseous form, so their partial pressure applied on the container where chemical reaction is taking place. So we had to write Kp now, Kp. So Kp equals to, again, it is pressure of ammonia. So I'm writing here an ammonia, and here we had two coefficients, so to the power 2 divided by constant pressure of nitrogen. Okay, and we have power 1 into pressure of hydrogen, and we have power 3 like this. Okay, so this is the relation for Kp. Okay, so here we have both the relation, it is for Kc and Kp. Now we know that by ideal gas equation, so I'm writing here by ideal gas equation. Ideal gas equation. By ideal gas equation. What we have ideal gas equation? It is PV equals to nRT. Here P is the pressure, V is the volume. I'm writing here P is pressure, V is volume. Then N is the number of moles. R is for universal gas constant, beta. It is universal gas constant. So I'm writing here universal gas constant. And T is the temperature in Kelvin. Temperature in Kelvin. Understood? PV equals to nRT. It is ideal gas equation.
Yes, sir.
Okay. Now I'm just transferring that V to other side. So what we'll have? We will have P equals to N divided by V into RT. Okay, this is the relation for the pressure, because here we have pressure, that's why we have to apply that. Okay, and we know number of mole present in a volume equals to concentration. Is it? Is nothing but the concentration. Number of mole present in given volume of solution is the concentration. Is it or not? Is it? So instead of N divided by V, can we write C here? Can we?
Yes, sir.
Yes. So P equals to, P will be, instead of N divided by V, we are writing C. So now we have C into R into T. So this is the derivation for any gaseous pressure applied by the reactant or product. It has been decreasing or increasing. We can calculate by using this formula. So now we have P equals to CRT. So C is the concentration. Okay, R is the universal gas constant and T is the temperature. So that we can apply for different reactant as well as product. So individually we can calculate pressure of, we have first ammonia. So pressure of ammonia NH3 will be what? So it will be, we have formula for that, the concentration into R into T. So concentration we have, it is concentration of ammonia NH3, right? Is it?
Yes, sir.
Yes. So we can write here pressure of ammonia NH3 equals to concentration of NH3 into RT. Likewise, for other reactant, we have nitrogen and hydrogen. So for nitrogen, we have P of nitrogen equals to concentration of nitrogen into RT. For hydrogen, we have P of H2. P of H2. H2 is the pressure of hydrogen. So it will be again concentration of H2 into RT. Okay. Now we have constant pressure also. Okay. So can we put all this value in that formula over here? Over here. Can we? Can we?
Yes, sir. We can do
Yes.
that.
Yes. Yes. Now we are going to replace the values there. So now we can write here. So after that, I'm using other ink so that you can differentiate easily. I'm using the blue ink now. Okay. So I'm writing here. So Kp for the reaction will be concentration of NH3 to the power 2 divided by concentration of NH3. It is Kp equals to NH3. No, NH3 done. Now we have nitrogen. So nitrogen,
N2.
yes, and H2. Concentration of H2 to the power 3. And we have RT here. It is the RT. So I'm writing here. It is R into T. Okay, and that see here over here. This is for the Kp beta. This is for the Kp. Okay, we have to put individual things here. See, we have formula before that wait a second, Kp equals to, we had constant pressure of ammonia, which is NH3 to the power 2 divided by pressure of nitrogen, okay, into pressure of hydrogen, it is H2, and to the power 3. So now here we had to place values here, here and here. So we have Kp equals to pressure of ammonia. Pressure of ammonia is that, is it NH3 into RT? So we had to write NH3 inside the square bracket into RT, and whole power we have 2 divide by, then we have, see, for nitrogen we have that value N2 into RT. So here we have to write pressure of, no, concentration of N2 into RT, and here we have for hydrogen that one. So here we have P of H2. So P of H2 is what? It is concentration of H2 into RT to the power 3, like this. Can we do that?
Yes, sir. We can.
Okay. Okay, so now we are going to solve further. Okay, so see here, it is already given the solution here. Kp equals to ammonia. Okay, so we have separated all these things here. Okay, suppose I'm going to separate that. So can we write here NH3 to concentration of, let me write here only, let me erase that. So we can write here, I'm just opening the bracket now. So Kp equals to concentration of NH3 to the power 2 into RT to the power 2. Can you write that? I'm just separating each and everything first. Here on that reactant, we can write here concentration of N2 into concentration of H2, okay, to the power 3. And see here, we have RT and here also RT. So RT into RT to the power 3. Is it?
Yes, sir.
Here we have RT and here also we have RT, but here we have to the power 3. So now we have separate written separately. So see, RT and RT is the base same, and here we have RT to the power 1 and here we have RT to the power 3. So their power will add here. So we can write in next step Kp equals to NH3 to the power 2 into RT to the power 2 divided by concentration of N2 into concentration of H2 to the power 3 into RT to the power 4. Can we write that?
Yes, sir.
Yes. Now here we have on react on the numerator also RT and on denominator we have RT. So now we are just transferring that RT to the power 4 on reactant. No, on
Subtract.
numerator. Yes. So their power will add and subtract. Yes. So Kp equals to NH3 in concentration form to the power 2 divided by concentration of nitrogen into concentration of hydrogen to the power 3 into RT 2 minus 4. So 2 minus 4 will be minus 2. Okay. So Kp equals to NH3 to the power 2 divided by concentration of N2 into concentration of H2 to the power 3 into RT to the power minus 2. So this is the relation for Kp. Understood? Understood, beta?
Yes, sir.
Okay. So now we had to write for concentration term. This is for the Kp. Now we have to write Kc. So I think we have already written Kc over here. See, this is the Kc one. What we have for Kc? It is ammonia to the power 2, concentration of ammonia to the power 2, and for reactant we had divided by concentration of N2 into concentration of H2 to the power 3. Instead of that we have Kc here. Is it? So can we write here? See, this is the term we have similar to that. Is it or not?
Yes, sir. Same.
It is equals to Kc. So instead of that, can we write Kc here? So Kp equals to, instead of that, I'm writing Kc here. So Kc into RT to the power minus 2. So this is the relation between Kc and Kp. Okay. This is the relation between Kc and Kp. So here Kp is what it is, equilibrium constant for gaseous reactant and product. Kc is the equilibrium constant for the liquid substance when we are using concentration of reactant and product. R is the universal gas constant and T is the temperature in Kelvin. Okay. Yeah. So here we have the derivation. So you wanna have like take a screenshot for that?
I wrote it down, sir.
Everything is done?
Yes, sir. I wrote it.
Okay. So in your like notes, it is given very directly. So most of the steps like been removed out. That's why it is complicated. But here we understood all the steps one by one. Is it?
Yes, sir. Understood.
Yes. Okay. So now we are going to understand about the Arrhenius concept about acid and base. Okay. It is again very important. Arrhenius theory says when any substance dissolve in water, okay, when any substance dissolve in water and it gives hydrogen ion, hydrogen positive ion, they are called as beta acid. It is according to Arrhenius, not by Hemant sir. It is according to the Arrhenius. That means again hydrogen positive ion is nothing but a proton. That means acids are proton donors. Proton donors. Is it?
Yes, sir.
Yes. And any substance when they dissolve in water and they releases OH negative ion are called as base. Are called as base. So those substances when they release as H positive ion are called as acid, and those substances they release as OH negative ion are called as base. It is according to the Arrhenius. So we can go through the point here. Acid are the substances that dissociate into water to give hydrogen positive ion, and bases are the substances that produce hydroxyl ion, means OH negative ion. It is the definition for acid and base according to the Arrhenius theory or Arrhenius concept. Understood first point?
Yes,
Easy
sir.
or very easy?
Very easy.
Yes. Second one. Now acids such as HCl and HNO3, okay, when they dissolve in water, they dissociate completely. They dissociate completely. Okay. And those acids when they dissociate completely are called as beta strong acid. They are called as strong acid. Suppose if you are taking 1 mole of HCl and you are dissolving in water, so all the H or like HCl will going to form H positive and Cl negative ion. Understood? So
Yes.
those acids when they dissolve in water dissociates completely are called as strong acid. Are called as strong acid. But few acid like acetic acid, when it dissolve in water, only partial, like only up to 5%, they are going to dissolve in water. Otherwise, 95% of acetic acid will remain undissociated. So it is not dissociating completely. So it is weak acid.
Sir, that means it will remain as acetic acid in
Yes,
water.
yes. Not in ionized form.
Oh,
Okay. Yes. So those acid, when they dissolve in water, they do not undergo complete dissociation, are called as weak acid. Very easy.
yes, sir.
Likewise, we have like bases also. Suppose we have beta NaOH. NaOH, it is sodium hydroxide. When we will dissolve in sodium hydroxide, will give Na positive and OH negative ion. That means all the NaOH will dissolve to form Na positive and OH negative ion. So they are called as strong base. Okay, but we have ammonium hydroxide like NH4OH. It is ammonium hydroxide. When we will dissolve in water, only part of it, okay, only most of the like NaO and NH4OH, it is NH4OH will remain 95% in undissolved condition, and OH negative and NH4 positive will dissociate only 5% of it. Okay, again, ammonium hydroxide is the weak base. They are called it a weak base. I hope you have understood that concept very well. Those acid or base, when they dissolve in water and dissociates completely, are called as strong acid or strong base. Whereas those acid and base, when they dissolve in water and they do not dissociate completely, are called as weak acid or weak base. Understood?
Yes, sir.
Easy or very easy?
Very easy.
Okay. Now we are going to understand about the next concept, and which is the conjugate acid base pair. Again, it is an important part. So a pair of acid base. Okay, we are discussing together acid and base. Okay, their pair, we are using the pair, means acid and base. okay, differ by one proton only. Only there is difference of one proton are called as acid base pair. Okay, only the difference is what? The difference of one proton only are called as acid base pair. So here we have the example. Okay, so suppose here we have beta acid. Which one? HCl, which is HCl. So when acid dissolve in water, okay, that hydrogen positive ion will release. Is it or not? Is it?
Yes, yes,
Yes.
sir.
So when, according to the Arrhenius theory, if it is releasing H positive ion, so it is called as beta acid, and it will give us Cl negative ion. Is it or not?
Yes, sir.
Yes. But when if HCl negative ion, that Cl negative ion is going to accept, see, it was releasing, and now it is going to accept H positive ion, will form HCl back. Is it?
Yes, sir.
Yes. So HCl donating H positive ion and Cl accepting H positive ion. Is it? So if it is donating, then it is called as acid, and it is accepting, so it is called as base. So here that acid and base are called as conjugate acid base pair. So here the difference is what? It is one proton.
Oh,
Understood the concept or still confusion?
understood, sir.
Okay. Now again we are gonna understand one more example for like acetic acid, CH3COOH. Okay. So again, if we will dissolve in water, it will gonna lose that H positive ion. Is it? No, that one, H positive ion. Okay, so will form CH3COO negative ion. Okay, on reverse, that will form like again going to react with H positive ion. It is going to accept, then will form acid back. That means it is accepting H positive ion, so it is acting as a base, and it is donating H positive ion, so it is acting as the acid. Again, it is called as acid and base conjugate pair.
Mm.
Okay, for base
Yes.
we can take example. Suppose I am taking NaOH. Okay, so when NaOH dissolve in water, gives OH negative ion to form Na positive ion. So that NaOH is donating OH negative ion, so it is base. It is base, but in reverse, that Na positive ion will going to accept OH negative ion to form NaOH back. So it is acting as the acid. So here you can say it is base and acid conjugate pair. Okay.
Yes, sir.
Yes. So this is all about the conjugate acid base pair. And here we have like n number of example. N number of example. You can go through that.
Okay, sir.
Yeah. Okay. So now we will discuss about application of Lacatlier principle of the industrial synthesis of ammonia. So wait a second, let me have water and then we will continue.
Okay.